Assalamualaikum warahmatullahi wabarakatuh, and good day to everybody. So my name is Abdul Hakim bin Saleh. I am a PhD uh, and working as a research officer here in USM in 2023 currently. Um, Thank you for having me, and thank you for joining this class. So for our first lecture, I'm going to teach you guys on the introduction to geographic information systems. So let's begin. Right. So the content of our lecture today is starting from introduction to GIS and a little bit of history, and I also touch on some of the current applications, current technologies that GIS is going through. The third one will be the geospatial data management, followed by spatial analysis, the data output, and the last one is the applications. Alright, a geographic information system, or simply GIS, is a type of database containing geographic data, that is, the description of phenomena for which location is relevant, combined with software tools for managing, analyzing, and visualizing those data. So this is the definition of GIS by Kang Sung Chang. So as I call it as K Chang. In 2016, he already published the ninth edition of the Introduction of Geographic Information Systems book. So like here, this one, I got the fifth edition. It is a very good book. If you purchase his book, you will get the a compact disc, a CD, or I'm not sure currently how is it, but the the activities inside this will also be given with the data, so you can follow through all the teachings, and also by the end of every chapter, uh, you will have the exercise using certain softwares. As in the fifth editions, in my case, I'm using ArcGIS. So he actually teach and provide the data to process. Okay, yeah, this is a very good book. So I am actually referring these lectures based on this book, and but the framework is a little bit different. So we are talking about data. So data basically is just an information, especially in terms of facts and numbers. So in each and every research works that we conducted, or some of the monitoring work that we conducted, we must have at least some facts or some numbers, some numerical values of what we collected from the site. Let's say, as in noise mapping, we requires at least in noise studies, we requires at least the value of the what we call this yeah, decibel. I'm sorry, the values of the decibel. So these are the things that we need to collect. But with geospatial data, that decibel values will be integrated with locations and the characteristics of the spatial features. So geospatial data is somewhat an extension of the typical data that has been collected, right? So from these locations, we can determine exactly where does this sound is collected and what are the surrounding lights, what are the surrounding is like, and at what time. In some cases, time also being incorporated. Okay, so therefore, the ability of GIS to handle and process geospatial data distinguishes GIS from other information systems. So the geospatial data here, let me recap a bit. It is a locations. So throughout this earth, if we simply collect data without any locations informations, you still can work with that data, but it is not to be said as a geographic information system kind of data. So with the GIS or geospatial data, right, you can plot actually all the data that has been collected in a form of maps, right? As you can see here on the right hand side, there are many layers that can be extracted from the most bottom layers, which is the real world. Okay, the most bottom pictures here is the real world, and you can extract the land usage, elevation, parcel, street, customers, for example, right? In order to study the noise, okay, the decibel of noise in this particular area. So you can stack all these layers together and do the analysis. There are many analyses that we can do in GIS. We will discuss that in towards the middle of this lecture. So digital GIS dates to the mid of 1960s when Roger Tomlinson first coined the phrase geographic information system. Many of the geographic concepts and methods that GIS automates date back decades earlier, right? That many of the geographic concepts and methods that GIS actually automates. So back then, all they do is actually they have the concept of GIS. They have already the concept of plotting or mapping, of course. Um, but to incorporate it into a computer system or digital system was first made by Roger Tomlinson in 1960s, right? So as we can see, it is not that old. This technology, this GIS technology, incorporating with computer is not that old, but mapping goes way back. Okay, mapping goes way back. All right. So to perform this digital GIS, they have several components that we need to have in order to conduct it better. So the first one is the hardware, followed by software, data, methods, and people. Starting from the hardware is of course the computers itself. Without the computers, it is actually not considered as digital. So, but the computers alone is not that strong in order to process a GIS. Therefore, it requires a networks. Okay, it requires a networks of of internet or a network of connectivity between computers. And the third one is peripheral devices, which is the plotters or printers. Plotters is actually the bigger version of printers. It can print up to A1, A0 size, not just A4 like printers or A5 like typical printers do. Then followed by the software, where we will have GIS software. There are many GIS software available in the market right now. But one of the earliest GIS software is made by Esri. It is called back then as ArcInfo, if I'm not mistaken. ArcInfo or MapInfo, right? And now it is called as ArcGIS. Right? There are also open source software, OS software, like Quantum GIS, GRASS, and many more. Last but not least, the database software. Okay, database software is very important too, especially when you are. It has many types, of course. It has many types of databases when we talk about database. But the most typical database software is actually has been integrated into the ArcGIS software itself, right? The small scale. But when we deal with a larger data or big data, it requires a much more sophisticated way to store all the data. So sometimes it requires a service of cloud, right? Cloud service, where all the data from many sensors will be dumped there, right? Followed by the data of GIS basically consists of these four types. First is a vector data, raster data, image data, and attribute data. So raster data, starting from raster data, is basically an image where you use day in and day out. It is a pixel image. It is simply a pixel image where you capture. It is that is what we call as the raster data. Is a pixelated data. But how about the vector data? If you are familiar with AutoCAD, right? AutoCAD is one of the easiest example of vector data where you can zoom the features that you have drawn. Okay, you can zoom the line, let's say, at whatever multiplication of that zoom, it will still looks as though it is not being zoomed, right? It is still in a form of a single line. It is not becoming a pixelated line, right? It will be just a single thin line. So that is how to distinguish basically between raster and vector data. So how about the image data right here? So image data right here is actually for references purposes. It is not really be considered as part of GIS processes. Okay, so although we will have many image data, but the image data, once you upload it or inserted into the GIS software, it is called as raster data. All right. So this is a example of image data. Image data is for references purposes. Okay. And the last one is the attribute data. So from the image data, usually it will help in producing some of the attribute data. So the attribute data right here is the information of the features inside the data. Let's say um, when we talk about roads, right? Um, roads actually bring a lot of attribute data, like the speed of the road, right? The speed limit of that particular road segment, um, the width of the road, the type, the material of the road. That are all called as the attribute data. Okay, so it is information of the either vector or raster data, right? Usually it will be an information of the vector data. Okay, and followed with the methods. There are several methods that we need to take a look into before we start any works. First is the guidelines. Secondly is the specifications, standards, and procedures. These are the references that we need to have before we conduct any works. Let's say for noise studies, we need to have standards, right? That were produced by the Department of Environment, right? On the noise. So from that standards, we can produce a map based on the classes of decibels that is provided by the DOE of Malaysia, right? So we can separate or classify uh, the data that we have collected into several classes. So these are the things we need to have: guidelines, the specifications, standards, and the procedures, the proper procedures in conducting the GIS work, data collection, and also processes. The last one, the last component of GIS is people, of course. Um, First is the administrators. If um, if you are an enterprise, you need to have an administrators to administrate everything. So below the administrators is the GIS technicians, the application experts, and the end users. So these are can say the users of GIS. But how about the end users here? The end users here is the person that is benefited from GIS, right? Perhaps they only wants the result of the GIS. They don't really process or do all the GIS works. So yeah, they still use GIS, but they only want the results. So these are the 5 components of GIS. Um, Everywhere and whenever that you want to apply GIS, these are the basic understandings. Okay, you need to have this. All right. Next, we go to the history of GIS. So one of the first known instances in which spatial analysis was used came from the field of epidemiology in the report on the march and the effect of cholera in Paris and the Seine Department, 1832. Sorry. So, yeah, um, as was mentioned previously, the computer, the digital GIS was first started in 1960s, but the mapping itself has already started way back, right? So in 1832, there is a proof that people have started using the concept of GIS. So this French geographer and cartographer Charles Picquet um, created a map outlining the 48 districts in Paris using half-tone color gradients to provide a visual representation for the number of reported deaths due to the cholera per every 1,000 inhabitants. Right? So this cartographer produces the map of the 48 districts in Paris just to pinpoint uh, the sources of the cholera, right? So with the death due to cholera disease, as shown here, the lighter color means that there are least death, while the darker color there are high number of death. So with this color grading, uh, the the health department of that time can take action, right, in doing something regarding this cholera outbreak. And it follows with the application of this kind of similar applications, right, followed in 1854. It is not that, yeah, just around 20 years. So in 1854, there is another outbreak of cholera, right, in Soho, um, London, right. So the middle here is the map of the cholera uh, outbreak in Soho. So as you can see here, the dotted line means the death, right? The death due to cholera. So as you can see here, right in the middle here, the death is very, very dense compared to this area or this area, right? Therefore, they notice that people in this center pumps their water from this like a fire hydrant things. All right, this is the water pump from beneath the ground. So back then they use underground water uh, to have their supply, but the underground water itself has been contaminated with cholera virus because of the influx of the people into this city, right, in Soho. So due to the influx of people in this city, people are moving in into this city. They are actually not prepared for the sanitary works. So all the cow dungs or cow sheds, um, all the slaughterhouse, everything was dumped into their drainage system. And without the proper sanitary works, they actually decided to clean all of this simply by pushing all the um, those things that I've mentioned, okay, the cow dungs and the blood and everything into the nearby river. So when the river is contaminated, um, it also affect the underground water. So this is the source of the cholera outbreak, right? So actually they are implementing a similar process to GIS, but without a computer. So this is some of the history and also the current technology of GIS that have been plotted. Um, as mentioned just now, these are the two earliest map that has been proved, okay, that we have traced back to 1840s, right? Which apply the concept of GIS, right? So and in 1840s also, um, French uh, scientists, as I can say, French scientists or photographers has already implemented the use of camera as a photogrammetry work. So photogrammetry is one of the data source for GIS. So we requires photogrammetry in order to do the mapping, do the tracing of that particular area, right? So it started way back in 1840s. Then in 1957, um, the first uh, positional satellite was sent into space, the lower orbit, right, by the Russian scientists. And this is the starting point of the GNSS, or we simply know it as the GPS, right? So we can determine our position based on the GPS applications. So the GPS applications is actually consists of um, several satellites, positional satellites, communicating one another to determine our position on Earth. So this is the first satellite in 1957, and just 3 years later, a desktop, right? A desktop is created, and also in 1960s, the as mentioned before, the first GIS, right? The first GIS work uh, related to digital GIS has been produced. So in 1960s, this is due to the desktop computer that is available. Before that, the computer systems is actually very huge. Not everybody will have its own computers, so there is no a personal computers back then. But in 1960s, once it has, um, the GIS has started to grow mushroomly, right? And similarly, in 1960s is the first internet for the networking has been developed, has been created by ARPANET, right? And not long after, in 1969, towards the end of 1960s, the born of the Esri. So as I mentioned before, Esri has produced a GIS software, and it was used since then, right? It is Esri is one of the pioneer of GIS, of digital GIS software, right? And then in 1988, the first remote sensing satellite has been launched by IRSO, which is the Indian Research, if I'm not mistaken, Space Organization. Okay, IRSO. So this satellite called as the IRS-A1. This is the first remote sensing satellite which capture the image of the Earth, right? Yeah, it has been produced by the Indian and being launched by the Russian at a space vehicles called as Vostok, if I'm not mistaken, right? Vostok. Alright, so this is until 1988. Then here, I'm not putting it here, should be about the year 2000. Okay, in 20th century, the development of in the early year 2000, the development of open source GIS software. Here is Quantum GIS. Quantum GIS is until today. It is one of powerful open source software. And also in 2004, there is OpenStreetMap, OSM. OpenStreetMap is a free GIS data that you can download, but make sure that you have checked the data over and over again before use it, because it is an open source data. People are contributing to that platform. Therefore, the accuracy might be might not be might not be that good. So yeah, please check. Although it has tons and tons of data, but you need to check it first. Right. And then in 2010, the client server application has started, where the internet is connecting all the clients of many devices of many users to the server. So online GIS has been produced right here, where you can use GIS software, online instead of installing it into your computer. Then in 2010 also, it produces the what we call this the integrated, if I'm not mistaken, the integrated GIS, where it actually communicating from one another, right? The client server is communicating from one web service to another web service. So this is also one of the biggest breakthrough in GIS software, right? Also in 2010s, people are not using anymore helicopters or aircraft for data collections. People has already moved into a much smaller version, which is called as the drone, right? Which is called as drone. So with 20,000 ringgits, or about $5,000 US dollars, you can have these systems, right? You can have drones and you can conduct drone mapping. Most of it has already been automated, so you don't need to understand, or you don't need to have a surveying or GIS background. You can simply buy and apply, right? Between 2010s and 2020s, the development of 3D model of GIS above ground and underground has been developed and studies over and over again, and also not just above and below ground. It has also of what we call as inside the building, called as the building information modeling. Some say it is part of GIS because it applies the GIS system also in BIM here, right? And also in between 2010s to 2020s, the development of smartphone applications is mushrooming, right? So there are many GIS-based applications available available in Google Play or Apple Store. Then this is the current technologies which we are using, called as the cloud GIS, where all the data is not being stored in the personal computer itself or the personal hard disk itself. Instead, we are always connecting all the data into the cloud, right? We put all the data into the cloud system, where we need to have the cloud provider, right? We need to have the cloud provider. So the advantages of having cloud compared to the personal computer hard disk is that cloud will ensure that the data is safe, right? And it is always available as long as you have the internet connections, right? So yeah, you can always conduct your GIS analysis without having any trouble regarding the breakdown of hard disk or any medium that you store your data into. And also the cyber GIS, which means the bigger version of cloud GIS. It is interconnecting from one platform to another. Cyber GIS is a very powerful system currently that we are heading to, actually. And the future of GIS is actually more on applications, or more on applications of sensors, right? Or the big data, uh, where all the sensors available throughout the country or throughout the earth, right? Uh, will send you the data every seconds, and the computer must be powerful enough, or the workstation must be powerful enough in order to process all the data, and uh, in order to analyze all the current conditions of that particular sensors. Let's say for earthquake, right? Earthquake requires many underground sensors, uh, which is planted in throughout the country. So any movement or any landslide that is occurring, right? Whether it is moved by 1 meter or even 1 millimeter, it will send the data into the cloud, and the processing hardware, which is the any sort of computers or the workstations, will process the data and analyze whether there is a sense of or there is a symptom of an earthquake is about to happen, right? So this system lets the computer to understand the situation itself, right? This is what we call as the machine learning, right? Machine learning. The big data provide the data into the computer, and the computer learns it, right? Whether the ground condition is still okay or not, right? And perhaps one day in the future, um, a noise data collector can also be spread out throughout the country in order to sense whatever noise that been produced by human. So the real-time data can be seen on the internet, right? On what is occurring right now and what is the condition, whether it disturbs the people or not, the nearby people. Other than that, once the machine has learned all the information by itself, it can assign a solution. It can provide a solution. It can recommend a solution on how to tackle the situation. Let's say um, by learning on the spread or the distribution of um, a plantation trees, let's say a plantation trees, a vegetation that we planted, we farming, right? The system can send to the machines here. This is the autonomous vehicles for agriculture, where it can do its works without any human operators, right? So this is part of GIS system where it can give instructions to these autonomous vehicles whether to kill some of the plant, or let's say the grass which shouldn't be in that farm area, right? Some particular intrusion grass or whatever. So yeah, this is we are heading into this technology, and also autonomous vehicles where there is no need for drivers, okay, to move from one place to another. Currently we only have the fixed one, which is the train, right? To full automate the vehicles, the personal vehicles is still under study, especially due to its safety. But all of these link to GIS. Right, let's take a 5 minutes break. Alright, let's proceed with our lecture. So next is the geospatial data management. So there are 5 points that I would like to highlight here. First is the aspects of geographic data, the data modeling, data acquisition, coordinate system and projections, and finally the data quality. So aspects of geographic data is any variable that can be located spatially and increasingly also temporarily. Sorry, not temporarily, temporally. Okay, uh, and can be referenced using a GIS. So, as mentioned before, geospatial data or geographic data is based on the spatial information, which is the position or the location, right? And it is not just that. The recent trend of the study has also incorporated the use of time. Okay, so the temporal data right here, the aspects of geographic data right here is actually refers to time. Okay, and all of that also, of course, must be reference to a single unit of GIS format. There are many GIS formats available, but we need to stick to one for our project. If we want to transfer it to another project, Yes, we can convert the format, but once we convert the format, we must convert everything, every data that we have, right, into that particular format in order to ensure the high quality and high accuracy. The locations or extents in the Earth space, right? Sorry, locations and extents in Earth space-time, okay, may be recorded as dates or times of occurrence, and the x, y, and z coordinates representing the longitude, latitude, and elevation respectively. So, how to explain the position? In order to explain the position of, let's say, your sampling point or the earth features, whether it is man-made features or the natural features that you want to collect, is represented with coordinates. The coordinates has a value of x, y, and z if it is a projected coordinates, or it can has a longitude, latitude, and elevation data if it is not a projected, if it is a geographic representation. Let's say, what is the difference between projected and the geographic? The projected coordinate system is the one that you have transferred the 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 round earth into a piece of paper. So you are actually distort the actual um, the actual surface of the earth, right? Earth is round, right? Let's say you have a ball and you want to cut part of the ball and make it uh, as though it is flat, right? It is very hard. So that's why we need to have a projection algorithm. So there are hundreds of projection algorithm available, but um, the the typical or the most commonly available is called as the WGS 1984, okay, World Geodetic System, uh, produced in 1984. So that system is widely available and widely understood by many GIS practitioners. So if you have a piece of map, right, that means you are actually has the projected coordinate system. But if you have a round globe, right, or you have a data of Earth, right, in the computer where you can turn around and look it in the form of 3D, then that one is called as the geographic coordinate system, right? GCS, geographic coordinate system. Let me show you. Let me show you. Right. So this is the Google Earth Pro. It is widely available right now. So what you see right here is the sorry is the geographic representation of positions, right? It's rounded and it is uh, explained in terms of latitude and longitude and also elevation right here, right? Let's say I click on one place, so it gives you latitude, longitude in the form of degrees and also the elevation here in altitude, right? There are several settings that you need to set before you will have the elevations. But the elevation information is right here, you can see, right? So this is the geographic coordinate system. So how about the projected? Projected, you need to go to options, change from decimal degrees to universal transverse mercator UTM, right? Click apply, click OK. So right now, the position has changed from latitude, longitude to meters, north meters, easting meters, and the elevation, right? And how about the map? Yeah, it's still represented as globe, but it's actually being projected, right? Now I show you. Let's go here and type projected versus geographic coordinate system. So let's take a look, right? Okay, so this is what the earth looks like, right? It's rounded, but the projected coordinate system is once you have flattened it. But as I mentioned before, it actually produces a distortion, alright? Distortion image can also be understood with I forgot to include it, but I hope it doesn't take a lot of time. So it's like this, okay? This is the geographic coordinate system, while this one is the projected coordinate system. It actually distorted the image, but it depends on the location. The very center of this projected map or image is actually quite accurate, right? But not all of this on the sides is not accurate. So you need to determine the very center area that you need to have, the type of projections algorithm that you need to use, right, in order to have an accurate position information. So this is the aspects of geographic data. Next is the data modeling. GIS data represents phenomena that exist in the real world, such as roads, land use, elevation, trees, waterways, and states. The most common type of phenomena that are represented in data can be divided into two conceptualization. First is the discrete objects. Secondly is the continuous fields. So the discrete objects is the vector, right? It's called as the vector. If we draw, let's say an AutoCAD, if we draw a point on that particular area, in the system base only understands that one point, right? If we draw a line, the system will understand only that one line. It differs with the continuous field. In an image, right? In an image, if you had an image, if you draw a single point on that image, the system need to still understand the whole image first and then the points that you have plotted, right? It is a continuous from one end to another. It is an image from top to bottom. Is still an image. So if you draw a line at the bottom, the system need to take a look from the top until the bottom, because it is a block of pixels. So these are the differences, right? Divided into conceptualizations of data modeling, which is vector and raster. Vector is discrete objects. If you plot it at one point, the system will have only that one point. Will have the coordinates and everything of that particular one point. But for raster, it is still a continuous, because it is like a piece of cloth. The system still need to take a look from the very one end to another end of that cloth or image, right? Next is the data acquisition, which includes several methods for gathering spatial data into a GIS database, so which can be grouped into three broad categories. So first one is the primary data capture, second one is the secondary data capture, and the third one is data transfer. So some categorize this as only two, primary and secondary data capture, while the data transfer is actually under the secondary data capture. But currently, the most recent understandings is to have three, right? That the data transfer is actually not under the secondary data capture. So let's take a look one by one. Primary data capture are those collected in digital formats specifically for use in a GIS project. So the key point right here is directly in a digital format. So once you capture the data, let's say you are using surveying work or you are using GPS, you plot that particular positions. Let's say the one point that we have been talking about, right? So the system will take that one point digitally, right? So that is the primary data capture. Raster. Raster, for example, it has also a raster in the form of digital formats, right? Let's say remote sensing imagery. Remote sensing is the satellite imagery that capture the surface of the Earth. Remote sensing has several bands, as we can see. It is I will talk about it later, right? But it is not simply as an image of RGB, red, green, and blue, just like your phone. It has much more than that, right? So the primary digital format of raster is the remote sensing imagery, which focus on spatial resolution, which is the pixel size, spectral resolution, which is the electromagnetic spectrum that are measured, and the third one is the temporal resolution, the repeat cycle of the collected images. So imagine the remote sensing is a space vehicles floating in the space, right? It is a satellite, but the satellite consists of multiple sensors, right? So one of the sensors is the spatial resolution sensors, where the more fine the sensors, the higher the resolution of that image. Imagine the remote sensing satellite is floating out of space, let's say 10,000 kilometers from Earth, all right, 10,000 kilometers, and capturing the image of the Earth. If you use your iPhone, if you use your Huawei, one of the top brand camera sensors available in the market, you still cannot see the cars, let's say, the buildings on Earth. You only see the shape of the country, right? This you only see the ocean. You with that camera, you couldn't see even a house, right? So, a remote sensing satellite has a very high-end sensors that can capture, and as you can see in the Google Earth I just showed to you, right? If I zoom in, this is one of the satellite imagery, but this one is the RGB, the red, green, and blue. This is the what we call as the true color, right? So we can even see a car, right? And the one of the highest spatial resolution available in the market is, if I'm not mistaken, about 0.3 meters resolution. It's very high resolution, right? It's very high resolution to capture everything available on the ground. So imagine, can your phone even have this? I bet not. If you are on the international space stations, okay, your phones cannot even see the houses, right? So this is what we call the spatial resolution. If you zoom in enough, right, you can actually see the image. Oops, has turned into a pixel. See these boxes, the straight line. This is the pixels of the image, right? It's very small. It's very high in spatial resolution, available for free. That's the best thing. Okay. Other than that is the spectral resolution, which is the electromagnetic spectrum that are measured. The spectral resolution of remote sensing is the colors that you couldn't see. Okay, it's the colors that you couldn't see. Let's say, what we call this, the night vision. The night vision. Some smartphone has already incorporated with night vision, where it can see in the dark better. So the night vision actually uses one of the what we call as one of the spectrum called as the near infrared. So this NIR or near infrared is allows you to see in the dark, but it is just a black and white colors, isn't it? If you take a look on whatever camera CCTVs available, in the YouTube channel perhaps, right? You can see in the dark, but there is no color. It is just a black and white, because our eyes cannot interpret, our brain cannot interpret what color is infrared really is, right? So we make of what we call as the false color. The RGB is the true color, while the infrared is the false color. We incorporate the near infrared or any other microwave spectrum or radio spectrum. There are many spectrums available, right? Into the RGB. We take that spectrum and put it into the RGB. That is what we call as the false color. So with the help of false color, we can actually conduct studies, right? Let's say the infrared spectrum is actually very helpful in determining the health of trees by looking at its water content, by looking at the disease that the trees has, right, from the satellite sensors on space. So that is the remote sensing, right? There are many. If I'm not mistaken, the freely available satellite image to be used, that freely available to be used, has about 20 electromagnetic spectrum. So you can study a wide broad of whatever happenings on the surface of the earth. All right, let's move on. The third one is the temporal resolution. The temporal resolution is the repetition of the satellites sensors to move to that particular place again. Right? Let's say currently there are one satellites is on top of us. One remote sensing satellite is actually positioned on top of us. That particular satellite will return back on top of us tomorrow at the same time. So that means that satellite has a 1 day cycle to reach Malaysia, right? But most common satellites, if I'm not mistaken, is about 2 to 3 times per day. So during the midnight here, like right now, it cannot take any pictures because there are no lights. Then perhaps in one in the noon and one in the during the dusk time. Okay, around 7 p.m. right, during the dusk, during the sunset. Right, so that means it has a 3 repetitions, a repeat cycle per day. So it depends. So that is raster. Next is vector. Vector is more on surveying. Okay, surveying, there are many. There are total station surveying. There are GNSS surveying. There are LiDAR surveying. Laser, 3D laser scanner. There are many. But all of them based on principles of 3D location of any point by using the measurement of angles and distances from other known points. So it's actually referring to a one known point, which is very accurate, and it transfers to the rest of that area, right? So if you use a total station, you will just be able to collect about about 1 point per minute, the fastest 1 point per minute, or 30 seconds per point. Yeah, if you use LiDAR, you can capture about 1 million points per second. Similarly, with the terrestrial laser scanner, about 500,000 points per second. Yeah, those are the surveying equipments. So all the points will be understand by the system in coordinates. It doesn't understand as though it is an image, a surface. It is not a surface, right? It is a point by point by point. So if there are many points, we call it as the point cloud. It is very time consuming, but is still the best way to obtain highly accurate point locations. The very time consuming here means the purple station survey. If we use the laser scanning, it is not that time consuming, right? But it requires a very high specifications of hardware. Okay. Next is the secondary data capture. Digital and analog datasets that were originally captured for another purpose and need to be converted into a suitable digital formats for use in a GIS project. Let's say uh, the first project has already collected all the primary data and they have used with their own objectives and aim, right? And then we want to conduct another project. Um, but the area perhaps is the same with the first project that was conducted. So we can communicate, we can ask the first project to share the data with us. So the one of the advantage of this is the cost saving and the time saving, right? We don't have to hire a new team to collect the same data, right? We just use of what the first project has conducted. But the data that has been collected in the first project has its own objective, has its own aims. Therefore, it might not suit swimmingly with our objective. They conducted a different study with us, but on the same area, on the same place. Okay, that's why we need to have some stages of checkings, especially in terms of the formats of the digital data formats, in terms of uh, the aspects of the collected data. Okay, some studies might not need all the aspects of a single features, right? They just capture, let's say, they capture only the front part of that particular features. While our study, we want the slide on the side. So it has several limitations to that. Okay. So as of raster, we can use scanners to scan the hard copy media such as documents, paper maps, film, and aerial photograph. So these are the primary. The listed here are the results of the primary data collection. Okay, so we use scanners like the typical scanners, just to scan the document, just to scan the available maps that has already been produced, right? The aerial photograph, the film, and so on. How about the vector? Vector requires a digitalization process of the scanned materials. So after we have converted the hard copy media into the digital forms, we can start with the digitization or the tracing process. Let's say we have an aerial photograph that we already scanned. So the aerial photograph shows the road network, right? But our GIS system, our own GIS project, doesn't understand yet the lines of the road. So what we need to do is to trace the line, trace the road, and register that particular line as routes. Okay, so that is what we call as the digitization. If we have buildings, lakes, we need to digitize the border of the features, right? Whether it is man-made features or the natural features. And we also need to be particular about the measurement error, whether the error came from the first primary data capture, data collection, or the error came from the scanning process. You know, sometimes the aerial photograph is very old and it's already been distorted, or the document is already being distorted. So that measurement errors need to be tackled. Photogrammetry is by taking photos, right? And the COGO means coordinate geometry data entry. So coordinate geometry is simply like the one that I said, the pinpoint, right? The pinpoint. You just um, register a single point, so the system will understand that that particular single points with coordinates and elevation and so on. It is not understand as an entire surface. So that is COGO. And the third one is data transfer. Data transfer was designed based on Special Data Transfer Standards (SDTS) to be a robust way of transferring Earth reference spatial data between dissimilar computer systems with the potential for no information loss. The SDTS specifies exchange constructs such as formats, structure, and content for spatially referenced vector and raster, including gridded data. Okay. Um, so when we talk about data transfer, the easiest way to understand data transfer is you are sending your image into WhatsApp group. Let's say you have a family group, you capture a selfie perhaps, right? Your daily selfie, and you send into the WhatsApp group. Okay. Your family members, which has a similar uh, computerized system or a similar smartphones as you, can have the uh, can look at the picture easily, right? That means it has a similar format, which usually to be JPEG. Okay, JPEG is a very common um, image format, digital image format, right? So when you send the data, your family members can see that particular um, image easily. But let's say when we talk about a very large data, let's say if you involve with photography, you will understand raw data, RAW data. Raw data is not understandable by many smartphones, right? Because it is usually from a digital camera, right? The mirrorless camera. So the digital camera or the mirrorless camera is sending you the data perhaps in a raw format, RAW format. So not many smartphones can understand that format. Therefore, the conversion from RAW data to JPEG data is critical. Okay, the conversion is critical. because there are many conversion algorithms available. Some conversions might reduce the accuracy of the data. Some conversion um, might miss 100% raw data. It might send in a JPEG format, which only accurate of up to 95%. So another 5% has already lost due to the conversion. So these are the things that the SDTS or the Spatial Data Transfer Standards put the guidelines to, right? So when we transfer a whole lots of data, the conversion, the transfer process, whether it sustain the structure of that data or not, is very critical. Okay, it is not as simple as transferring image. It is not as simple as by using your external hard disk. No, it has its own way to transfer to make sure that the data uh, is 100% similar from the source. Okay. Next is the coordinate systems and projections. The Earth can be represented by various models, each of which may provide a different set of coordinates for any given point on the Earth's surface. As more measurements of the Earth have accumulated, the models of the Earth have become more sophisticated and more accurate. So, the coordinate systems and projections is actually has been touched. The coordinate systems means the geographic coordinate systems, while the projections is the projected coordinate system. So I believe you can recall of what was mentioned with the image that I've searched for you guys. Right. Um, in reality, there are many models. There are hundreds of models. That's why whenever you want to share the data, you need to make sure that another platforms has the similar models, has the similar system understandings. Okay, so I already explained all of these actually. On the second point means that due to the uh, accumulated measurements, let's say uh, in Kuala Lumpur, in a major city of anywhere, let's say, uh, many studies and many data has been collected by certain companies. So that companies usually use the data only one time, right? They doesn't store the data in their own server due to space limitations. Therefore, they are just sharing the data to the um, giant web service like the Google Earth, right? So they are storing the data there so that other people can use it. So the data that has been collected is the most recent data, which makes everything becomes more sophisticated, right? The accuracy has become much higher. Therefore, it has its own way of storing the data, and it will become when it reaches you, the end users, it is a more accurate data. Okay, you can have more accurate data by time. Let's say in 2030, yeah, perhaps you can have the one that I mentioned, the 0.3 spatial resolution, right? Images. So there are models called datums. The sorry, right. Once they have accumulated all the models, they can produce a much more sophisticated and more accurate models. And one of the models called as datum or geodetic datum that apply to different areas of the earth to provide increased accuracy. So our common geodetic datum is called as WGS 84, the World Geodetic System 1984. I have mentioned about this. Um, so it is commonly available and you can use it worldwide. So the main purpose of this is to standardize everything, every uh, every data that has been collected by other surveyors, by other GIS technicians, right? They use the same platform. So geodetic datum is a global datum reference or reference frame for precisely representing the position of locations on Earth. Okay. Next is the data quality. No digital model can be a perfect representation of the real world. It is important that GIS data be of a high quality as GIS accuracy depends upon the data source. So um, here we can say the data quality is very important in order to make sure that the GIS output is of a very high accuracy. So we can say that if you have rubbish data, you will have a rubbish output, GIS output. Whether your processes is very sophisticated, is very detailed, is very high end, and most recent processes that you have used, but if the data, the starting data is rubbish, then the GIS output will be also rubbish. That's why the data quality is very important to ensure that the output is of high quality. So therefore, there are several elements in ensuring the data quality. First is the accuracy of the data collected, the precision of the data collected, the vagueness, completeness, currency, consistency, uncertainty, and propagation of that uncertainty. Okay, let's take a look one by one. First is the accuracy. Accuracy is the degree of similarity between a represented measurement and the actual value. Thus, the error is the amount of difference between them. There are positional accuracy, which is represented by X, Y, and Z. Attribute accuracy, the validity of information. Let's say the width of the road. If we talk about roads, the width of the road, the speed limit of the road. So if the speed limit of the road is 90 kilometers per hour, but in the attribute is stated as 60 kilometers per hour, that already has an error right there. Okay, and the last one, the accuracy is on the time, right? The actual date and the time taken of that particular data is very important. Okay, it's very important. Okay, next is the precisions. Precision is the degree of refinement in a represented value. The degree of refinement. Resolution is a commonly used expression of positional precision, especially in raster datasets. So these are the raster datasets. Previously, it was 250 meters per pixel. So this one pixel, one end to another, is 250 meters. So you can see nothing here. And let's say with this accuracy, you will ask, okay, show me building A. You will not be able to show anything right here because it is simply a black and white. Okay, so you will not be able to pinpoint any building right here. So not the most, a more recent satellite imagery after this 250 meters is the 30 meters resolution. Still, if we ask, please pinpoint the location, the position of a building A, you still unable to manage to pinpoint anything with this because it is still pixelated. Okay, it is not clearly seen. Then a more recent with 10 meters. With 10 meters, oh, you can see already. Or this is building A. Building A is stated is right here. So then the next question is, which part is the entrance of this building? Nah, you still cannot state which part is the entrance. And one of the most recent imagery is 1 meter, right? As available in the Google Earth, as provided by the Google Earth, it's 1 meter. So this 1 meter accuracy, you will be able to determine which is the entrance of this building, which is where is the parking lot and whatsoever in more detail. Perhaps a more detailed satellite imagery in the future will tell you where your car is being parked on. You know, where is your car? Perhaps you have a missing car. Yeah, excuse me. So this is actually yeah, it's not reaching. Anyway, yeah, that is on the precision. Next is the vagueness or obscureness, the degree to which an aspect or positional attribute and time of the phenomenon is inherently imprecise rather than the imprecision being in a measured value. So the vagueness is actually on how sure, not how sure are you, is actually on the the determination of the the values on the data itself. Okay, let's say I show you right here. This is one of the GIS technology where it can detect the crown of the palm tree. So in other words, it can count the palm tree easily, right? And produce a map like this one. So it can automatically count the number of palm tree in this farmland, right? But how about this one? Uh, let's say the question is how many um, durian tree? How many durian tree in this forest? So perhaps the system can detect a certain form of canopy, let's say, or this one, and this, and the combination of colors and whatnot, right? But how determined the system really is in telling you that yes, there are only 5 durian tree in these photos. How determined if is the system? Because the colors might be different from one durian tree to another, depends on the type of durian, right? And other trees might also have a little bit similar colors at one stage with the durian tree. And also the role of the sunlight, whether it is bright or cloudy, also plays a role in determining the type of the trees. Okay, so these are the vagueness or the obscureness of the data. To ensure the data quality is high, it is best to have this kind of data, the palm tree kind of data, not this kind of data. Of course, this is just an example. It can be implemented in many other way, okay, in many other features, right? Next is the completeness. Completeness is the degree to which a data set represents all of the actual features that appear to include. For example, if a layer of road is missing some of actual roads, it is said to be incomplete, right? So the completeness usually requires an on-site visit, right? An on-site visit or reference from multiple web service platforms. Okay, let's say the Google Earth. Not the entire Google Earth has the same satellite imagery. Okay, some Google Earth, some part of the Google Earth has a more recent and some part has a backdate satellite imagery. So you need to make sure that all the data that is collected on the Google Earth, if you are referring to Google Earth, all the data on the Google Earth is the recent one by simply going to the site, by visiting the site. Because if you claim that the data is recent, yet it doesn't include any recent features that has been constructed on that site, then the data is actually not complete. The data has a missing features. So these are the things that you need to make sure when you are taking or you are referring to other documented data. Okay, and the currency. This is kind of related to the completeness. The currency is the most recent point in time at which a data set claims to be an accurate representation of reality. This is what I meant. I've captured these photos in Kuala Lumpur, Malaysia, right? Although it is still in Kuala Lumpur, but the year of the satellite imagery is different. The year in a high building density area or the city center is much more recent compared to the area which is the outskirts or the outside of the city center, because it is not the priority. The priority is the area which is consistently developed, right? Okay. So this is the currency. The consistency is the degree to which the representations of the many phenomena in a data set correctly correspond with each other. For example, will the shortest path be accurate if some of the road connection is not consistent in terms of its connectivity with each other? For example, here, let's say from point 1 here, this is point 1 to point number 2, and this is the shortest path analyzed at the first one, okay, at the first run. Um, how how to tell you this? Let's say uh, the data quality, okay, the data quality of this shortest path isn't the best one because um, it is identified later on that there are missing road connections here. In some parts here, there are missing road connections. Okay, perhaps the shortest path should be like this. Perhaps, okay, the shortest path should be like this. But due to some missing or unconnected lines right here, then the system produces a shortest path as shown here. This might be correct, and this might be correct if all the lines are well connected, but this also might not be true and incorrect if some of the lines are actually not connected with one another. So the consistency means that the connectivity of these lines, as in this case, right, of these lines. The uncertainty. Uncertainty is a general acknowledgement of the presence of error and imprecision in geographic data. Sorry, I'm reading this while I'm thinking. Okay, a general acknowledgement of a presence of error and imprecision in geographic data. In short, it is a degree of doubt, right? It is a degree of doubt or doubtness. It is difficult to know exactly how much error is present in a data set. Thus, some form of estimate is best to be attempted. Okay, so if you receive a data, you have seen that data in several platforms, right? You have seen the data in several platforms, this data of the same area, and you take a look at the data, and suddenly when a new data was sent to you, you have a little bit doubt if the data doesn't consistent or the data doesn't really match with your experience of that particular data. Okay, that uncertainty must be addressed. Okay, so how to address that uncertainty? There are several ways. You can hire a GIS technician in order to take a look back at the data, whether it is fit with the fit with the actual or the reality, the actual condition or the reality of the data. Okay, so that is the uncertainty. There are many steps that you can use to estimate. Right? If you purchase a data and then you take a look at the data, you will have some sense of doubtness on how the data is or should be. Okay, right. So that's why it is important for you to do a background study of the area that you want to study. Okay, and the last one is the propagation of the uncertainty. This means the degree to which the quality of the results of spatial analysis methods and other processing tools derive from the quality of the input data. Okay, so yeah, it can be understood simply by reading this statement. Okay, with that, we will have a 5 minutes short break before we go to the last part of our discussion. Need to charge my phone. All right. It doesn't move. Come on, move. That's right. Okay. So next is the spatial data analysis. This is the interesting part. Okay, because you can have some sense of what analysis that you can do with GIS. Okay, right. So the first one is the terrain analysis, followed with the proximity analysis, topological modeling, network analysis, cartographic modeling, map overlay. This is very common, map overlay. Geostatistics, one of the famous. Multi-criteria decision analysis. This is good for master study. And the last one is GIS data mining. This one is on the data analytics or whatever involving with big data. Right, let's go one by one. First is the terrain analysis. Many geographic tasks involve the terrain, the shape of the surface of the earth, such as hydrology, earthworks, and biogeography. So terrain usually in the form of a raster digital elevation model, simply called as the DEM. You need to remember this one. DEM is commonly talked about, right, by many experts, or a triangulated irregular network, TIN. So this one is more, when we talk about TIN, it is more on engineering, okay, the actual construction engineering rather than the DEM. DEM is more on GIS. So some of the most common analysis include slope or grade. Okay, this is the analysis under terrain analysis. So by studying the steepness or the gradient of the terrain, okay, the steepness of on the side of a hill or an edge, right? Whether the steepness is still stable, whether the steepness is suitable for vehicles to pass through, whether the steepness is is uh, is suitable for a rescue team to go through the terrain. So the gradient can be presented in terms of usually in terms of percentage and the degrees, right? But most of the people use degrees rather than percentage. Next is the aspect. Aspect is the direction in which the terrain faces in degree from north. So aspects is very good, especially when you want to study on which directions does one surface of the terrain is facing on. Okay, um, yeah, you can use aspects in the study of the water flow. Okay, in the study of even noise propagation, it bouncing. How does it bounce from one wall to another, based on the aspect or based on the direction uh, faces of the hill. In which direction does it face? Okay. Next is the cut and fills. Uh, this is uh, this is familiar, especially for engineers, civil engineers. Cut and fills is the computation of the difference between the surface before and after the excavation work or the excavation project, just to estimate the cost. Right. This is very important for project managers to uh, to study the budget before any construction works even started, right? Whether it can be zero waste, you know, it it the engineers might cut one portion of the land and fill another portion of the land without having any additional from the outside, or without having to uh, to 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 remove any of the soils other places on other place. Okay, uh, yeah, that is a cut and fill. So how many excavators does it requires? How many dump trucks or the trucks requires to move the soils? All of that is the cost. So cost is very important. If you hire only one dump truck and one excavators just to, to cut the cost, the while the dump truck is doing their work, the excavators can rest. So that is actually a waste of budget, because the dump truck need to go from one place to another with all the muddy surfaces. Is very hard and time consuming. So you need to budget everything to be a very efficient uh, work progress with a good cost estimation. So this is where terrain analysis can help you with. Okay. Next is the hydrological modeling. Is the analysis involving watershed or the catchment area. So in which direction does the water flows from the top of the hill if there is a rain, and where does the water will accumulate, uh, and perhaps causing floods, flash floods, or has increased the risk of landslide and much more, right? Or the sediment transport analysis can also use the hydrological modeling. The viewshed analysis predicts the impact that terrain has on the visibility, right? The viewshed is actually, if it can be understand with, if you are standing on one point and you are looking at a view, right? Let's say there are a new landfill site is constructed on your area. So whether from your house you can directly see the landfill site or not. So that analysis can be done by using the viewshed analysis. From your point of view, from your house, will you able to see that landfill site, or the landfill site is behind the hills, or some of the hills is actually covering you from seeing that landfill site? So that is the viewshed analysis. And the last one is the one of the simplest, is the shaded relief. Shaded relief is just to increase the uh, the understandings of a 2D imagery, as though it is a 3D model. So if you take a look at a map, you will not able to see which ground is higher than the other. A general map, okay, or a general aerial photograph, you will not be able to see clearly which area is higher than the other. So that is where the shaded relief plays its role. It can enhance the uh, the 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 ground height with the shades of the sun. It will provide you with shades of an artificial sun that is created. So you can see a 2D images as though as it is a 3D model. Okay, that is the terrain analysis. Next is the proximity analysis. Is one way of analyzing locations of features by measuring the distance between them and other features in the area. Okay, the distance between point A and point B may be measured as a straight line or by following a network path, such as street networks. These include buffers, multiple ring buffers, and tiered polygons. Alright, so proximity analysis, the most common analysis that we use is the buffer analysis. So I will highlight on the buffer analysis. Buffer analysis is an area of buffer. Okay, let's say whenever you take a look at a train network in a first world country, right, or developing country, like Malaysia is a developing country, and I believe in China is a first world country, America is a first world country. So if you take a look at those countries, railway track, okay, the railway track on the side of the railway track, there are buffers. Okay, there are buffers where people cannot pass through that area. The buffer sometimes is, has fences, right? So it prevents from other people to move into the train track area. Okay, compared to, let's say, in Philippines, compared to, let's say, in India, I believe some part of the country is similar to the first world country, I believe, but the media usually highlighted some of the area where there are no buffer. People can walk over the train railway. And in Philippines, if I'm not mistaken, the railway track is actually passing through the markets, right? The markets. So that is where you can understand the functions of the buffer really is. Okay, so let's say some of the buffer analysis that you can produce is you want to know whether within a kilometer distance from your house, whether you can reach the closest grocery stores. Yeah. So you produce a 1 kilometer buffer analysis. And then if the grocery stores is within the buffer distance, then it will be highlighted. Okay, so that is the buffer analysis. And multiple ring buffers, let's say 1 kilometer, you can have another 2 kilometers, 3 kilometers, 4 kilometers in order to take a look. The tiered polygons is from one point to another. It has a relationship in terms of its distance. Okay, and if I'm not mistaken, it also involved with the weighted of that particular points. Okay, so you can study more on the tiered polygons. It's widely used but not as wide as buffer analysis. Next is the topological modeling. Topological modeling is a very powerful tool. It helps you a lot, right? So topological relationships allow complex spatial modeling and analysis to be performed. This modeling understands the relationships between geometric entities traditionally include adjacency, means the adjoins between features, the containment, the enclosures between features, and the proximity, distance between features. So it helps in reaching full consistencies of data. So as mentioned before, in the consistency data quality, right? Where I show you the shortest path, the data is said to be inconsistent if there are many lines that are actually not connected one to another. There are many roads in the system that are not connected one to another. So topological modeling can help with that. Okay, it can detect which, it has many rules. Okay, you can select the rules. So whether you want to have a connected lines, so it will run through that area and detects whichever lines that is not connected. It seems to be connected, but it is not. So that is the topological modeling. So it's very important, especially if you have, as stated here, complex spatial modeling. If you are studying a road network, the road network of the whole Kuala Lumpur or the whole major cities, where the road itself is like is more dense than a spider web, right? So one line to another need to be connected, right? Next is the network analysis. There are several types of network analysis. Point-to-point analysis is the most basic. It consists of a set of points to find the route based on specific criteria. Some common analysis using point-to-point analysis is the shortest distance, fastest route, optimal route, least cost path. So shortest distance is based on the distance itself, between 1 kilometer and 0.8 kilometers. So it will prefer the 0.8 kilometers. Fastest route. Sometimes the 1 kilometer is the straight route and 0.8 kilometer is a shortcut. So that means it windy, right? So the fastest route will be chosen, which is the 1 kilometer distance. The optimal route. Optimal route is based on the rules that you have set. The rules that you have set. Perhaps you have set the rules to be not to be the shortest and not to be the fastest. So it is an optimal route. So it will give you the optimal route. And the last one is the least cost path. You can put each distance as cost, each kilometer, each meter in distance as the cost of fuel consumption, perhaps, right? As the wear and tear of the tire, perhaps. Okay, so the lesser the cornering means the lesser the wear and tear of the tire. So you can find the route with less cornering, less junctions with the least cost path. And the least cost path usually in the form of raster rather than vector. Finding coverage, the second analysis, finding coverage. The drive time areas correspond to the distance that can be reached within a specific amount of time, right, in a service or the appointed area. So this more on the drive time with the time window, as we can say. The truck need to arrive at that place between 1 to 2 p.m. between the lunchtime. Let's say a food truck. That is the time window of that area. You need to supply the food, all the foods between 1 to 2 p.m. Let's say, or 12 to 2 p.m. Okay, so so we want to find the drive time areas of that particular place, means that service area. Next is the optimized fleet. minimize overall operating costs by managing sets of vehicles and drivers. The purpose is to find the most efficient route for delivery, repair, transit, or any type of fleet services. This is easily understand with, let's say, a courier service, as in Malaysia is Post Malaysia, Post Berhad Malaysia. We also have JNT. We also have, I'm not sure about FedEx. FedEx is more on America. Yeah. So how to optimize all the fleets? We don't want one vehicles or drivers to have the items of other service areas. We don't want that. We don't want 100 vehicles to service in one area. We want to spread it. So how to spread it? How to optimize the fleet? Perhaps this one truck only covers one part of the service area, and there are many service areas. This one truck covers only one part, and what I'm talking about. Perhaps there are many service areas. Okay, just understand that. And the first service area requires 3 vehicles. The second service area perhaps only requires 2 vehicles. So these are the things that what optimized fleet is meant to do. The optimal site to locate the best location of given facilities. So one of the functions is location allocation. This helps business owners to pinpoint optimal location for their new stores. So it is a way to determine the best locations based on roads connectivity. So if the new stores or new grocery stores, hypermarket, supermarket, has a higher density of roads, means it has a higher demands. Perhaps it is easily accessible. It is not too far from the housing area, perhaps. Okay, so this is the optimal site. And the last one is the OD cost matrix, origin destination cost matrix. Measures the least cost path from multiple origins to multiple destinations. So unlike the optimized fleet, it is from one location to many service areas. This origin destination is based on multiple places, multiple origins, okay, multiple depot to multiple destinations, right? So yeah, that is the OD cost matrix. Next is the cartographic modeling. It refers to a process where several thematic layers of the same area are produced, processed, and analyzed. Cartographic is a crafting the appearance of a map, applying the principles of design and knowledge of how maps are used to create a map that has both aesthetic appeal and practical functions. So as you can see, on the left hand side is the Napoleon War map, if I'm not mistaken. It is between France and Russia. So the map doesn't really shows any what we call this, any earthly representation, any locations. When you take a look at the map, you couldn't understand where on earth is this, right? But the map has its purpose, which is to show the movement of the military troop from France, if I'm mistaken, from France to Russia. And after the war with Russia, it returns back to the to France. So the amount of troops, the number of troops is very huge departing from France. As you can see there, it is very wide. It's very wide. Okay, but once it returns, it's very thin. That means this is the only amount left after the war with Russia. This is the amount of the soldiers left. So this is the position, this is a location, a location, a location, a location. Throughout this journey, there are many casualties already. Alright? Once it reach Russia, it's only this amount, and it doesn't take much. It just return with the same amount, it surrender, and it need to walk back, and many casualties also until the end. So this is one of the famous cartographic map showing the war. This one is the, if I'm not mistaken, is the cartogram or the transit map. Alright. This is the bus services in Kuala Lumpur, Malaysia, where it doesn't really shows the geographically what we call this like on earth, right? These roads, there are no roads like this, right? Very straight line and one another, very close one another. No, this is just to make things easier to understand. Just at one look, right? You can understand which line you need to take by the color representation, and the color representation, the shapes represents the area that it passing through, and it has several interchange lines right here where you can change buses and so on and so forth to go from one destination to another. So this one is easily understood rather than if in the actual geographic representation. Okay, geographic representation is the scale is not important in these terms. Okay. Next is the map overlay, which is the combination of several spatial data sets, points, lines, and polygons, which creates a new output vector data sets, visually similar to stacking several maps of the same region. So let's say from the orthophotos, which is an aerial photo obtained from photogrammetry work, you overlay it with a parcel framework, overlay again with the ownership text parcels. So this is the key point right here. Overlay with the addresses, rights and interests, administrative areas. So let's say the administrative areas of that area. Let's say in Penang, in USM, Nibong Tebal. So the Nibong Tebal administrator or Nibong Tebal authority, in other words, can collect the tax from the ownership of these parcels. So just by overlaying these layers and layers of data, you can understand how many taxpayers that are actually not paying the tax, how many ownership that are not actually paying the tax. If they are paying the tax, many other studies can also be detected. So the local authority can work more efficiently by understanding the distribution, right? Perhaps the the highest tax payer that actually pay the tax is on the lower demographic income, let's say, right? So that shows something interesting there. What happened with the rich people there? Okay, do they not paying the tax because they are not satisfied with the service provided, and so on? Okay, so a more efficient work can be provided, can be conducted. Next is the geostatistics, one of the famous analysis. Geostatistics is a branch of statistics that deals with field data, spatial data with a continuous index. It provides methods to model spatial correlation and predict values at arbitrary locations, such as using the interpolation methods. Okay, so what does this mean? Is that, as you can see here, there are points right here, there are points right here, there are points right here. So between these 2 points, let's say between these 2 points, left and right, there are no points. There are no points right here. Between these 2 points, there are no points right here. So how to understand the data between this 1 point, or between these points, or how to have the approximate data in this center, in this middle, in this area where the data has not been collected. Okay, so it can be distributed or it can be interpolated by using the geostatistics analysis. There are many geostatistics analysis. The IDW, inverse distance weighting, where the further the distance, the longer the distance, the lower the value. The closer the distance, the higher the value. Let's say, as you can see right here, okay, the value right here is in orange color. Okay, it is because it is very close to the sampling point, but the further the value right here, it has already changed to green, right? And in relation to this very dark green, it changes this yellow to greenish, although it is very close to the sampling point, right? So these are the interpolations. Apart from the IDW, is one of the most sophisticated interpolation is called as kringing interpolations, where you need to have several information before you run the processes. You need to insert the correct information. If not, it will produces less accurate data. Next is the multi-criteria decision analysis. If you would like to further your study into Masters and PhD, this is a good option to apply. So MCDA methods support decision makers in analyzing a set of alternative spatial solutions. MCDA uses decision rules to aggregate the criteria which allow the alternative solutions to be ranked and prioritized. Some of MCDA methods are analytical hierarchy process, which I use in my own PhD work, and analytical network process, a more complex version of AHP. Right. So MCDA here is actually just like it is not similar, just like the questionnaire, where you obtain the decisions from the people and you change from the qualitative data to the quantitative data. You change from opinion to a numerical data. So it has the same concept, but it only focuses on the decision makers, right? The higher rank. It does not base on the the amount or the number of uh, the surveys. It depends on the decision that we made based on the multiple criteria that we have located or positioned for that decision makers to make a decision. So the results of the MCDA is actually the rank of all the criteria that we have listed. So the rank process is based on the decision makers, and um, the rank is in the numerical form. So that from that numerical data, we can implement it into a GIS and conduct any studies that we want to. Alright, the best part of AHP and ANP here is actually it has the inconsistency, it has a consistency ratio, okay, where it detects if um, the decision made by the decision makers in rank the criteria, whether his or her opinion is consistent or not. Okay, if the value of consistency ratio is not exceeds the limit, then we need to reject the opinion of that decision makers. So that's the best. So we will only have a consistent data. Next is GIS data mining, also known as spatial data mining, which is the application on mining of spatial data, such as the monitoring work of environment. It is a partially automated search for hidden patterns in large database for potential GIS-based decision making. A characteristic of such applications is that spatial correlation between data measurements require the use of specialized algorithms for more efficient data analysis. So this is data mining. Data mining is simply by looking at thousands and thousands or perhaps millions of data and find the similarities or find the patterns or find the relationships between one data to another. If you go shopping at your nearest hypermarket, right? Usually they will give you a member card. Okay, they told you that the member card will give you vouchers, but what really happened is actually they are data mining your purchases. So what do you buy on the beginning of the month, and what do you buy during the winter, during the cold weather, what do you buy during the hot weather. So your purchases is being data mining by the hypermarkets in order to in order to provide the the the, the products that you purchase during a certain time. Okay, perhaps during the full moon, suddenly many people of that area eats uh, instant noodles, let's say. So during the full moon, every month, the hypermarkets will provide a voucher for instant noodles. The hypermarket will provide many types of instant noodles during that time. Okay, all right. That is what we call as data mining. So in GIS, forget about instant noodles. In GIS, it is more on the relationships between one feature to another. Let's say you are mining the data of Earth vibrations. Earth vibrations of some particular area increases during a certain part of the year where the rainfalls is at at higher amount. The amount of rainfall is at its peak, let's say. So they can study that and relate one to another in order to provide a single decision that is in order to be prepared if any disasters hit. Okay, I think forget about the short break. The last one is the data output. I shouldn't put the short break. We just had the short break. Okay, so the data output. Non-cartographic forms of GIS output are tables and charts containing spatial and non-spatial attribute information. Okay, just like any other statistical data, just like any other data, while the most common form of output from a GIS is a map. So there are basic elements of a map output: title, legend, map scale, north directions. Okay, the title of the map. Here, the title of the map is actually Travel Malaysia. Okay, the north direction should be in that direction. Okay, the map scale here, right here, usually it will be at the bottom. Okay, every 1 centimeter here represents I don't know 50 kilometer. I'm not sure, right? And the grid, coordinate value, metadata, ancillary text, float maps. So yeah, these are the basic elements. Okay, the most basic is the first one: title, legend, map scale, and north directions. Legend, by the way, this is the legend. Legend tells you the meaning or the definition of all the symbols, all the colors right here. Right. Next is the grid, coordinate value, metadata, ancillary text, and float map. This is the second level of basic elements. It is more sophisticated, more complex. So grid is the vertical and horizontal line, which represents which tells you the divisions of the study area. Okay, so at the end of this grid, usually it will have x, y, right? The coordinates. Sorry, not x, y. The vertical is y, not x. The horizontal is x, not y. So it will give you x1, x2, x3 right here, the coordinate values. y1, y2, y3, and so on. Okay. And the third one is the crucial one, which is the labels, symbols, and colors. Okay. The labels, let's say this state name, Perak, Kelantan, Terengganu, Selangor, right? The symbols here, the red dots right here, if you can see, the red dots, what does that mean? And the colors. The colors should be aesthetic. Means, in modern cartography, people usually prefers to have a pastel color, right? And by the way, this is what we call as the float maps. Okay, It shows where Malaysia is on Earth or on the world map, right? So pastel color means the color is not too vibrant, not too high in contrast, not too uh, what we call this? The brightness is not too bright nor too dark. Yeah, that is the pastel color. Okay. The data output, the last point, the data output could also be in digital form, especially for web mapping. Okay. If you search for Google Maps, okay, that is actually in a form of web mapping. The last one is the applications. Okay, the applications of GIS can be classified in several ways. First is the goal, either scientific research. First is the goal. Okay, there are many ways to classify this one. On in terms of the applications, but as what I refers from Wikipedia here, it classes like this, right? First is based on goals. So either scientific research to discover new knowledge or resource management, which mean to apply the knowledge to make practical decisions. Okay, either use the GIS applications is for scientific research, is to find something that is new, and also another one is the resource management, which is like the non-government company, all right, to apply that findings into the real world, okay, into a practical decisions. Next is the decision level, whether it is strategic for long-term and visionary decisions, or tactical, which is the medium-term decisions to achieve strategic goals, and also the operational level, which is the decisions concerning with day-to-day tasks. Next is the institution, implemented in a variety of institutions such as government, which starts from the municipal to international level. Okay, for business institution of all types and sizes, non-profit organizations, the NGO, the NGOs usually, which does not require any profit, as well as personal users. Okay, the lifespan, focus on a project which focus on accomplishing single task, or an enterprise which intended to be a permanent institution. Next is the integration. Traditionally, most GIS applications were standalone, based on your own PC and your own hardware software. But in present day, geospatial technology was merged into broader enterprise applications, sharing IT infrastructures. It has its own storage, but it sharing with another storage. Okay, sharing IT infrastructures, databases, and software using integrated platforms. That's why if you use the Google Map software, the Google Map web service, you don't need to install the Google Map itself. It's just there. You just search for it. Okay, that is the result. One of the result of the merging of enterprises applications. And the last one is the topic. Okay, there are many in terms of topic. All right, so the topic is the domains in which GIS is applied concerning human world. Okay, the first key point is the human world, such as in terms of economies, in terms of politics, like geopolitics, in terms of transportation, education, landscape architecture, which uses the functions of viewshed analysis. The archaeology uses 3D representation. Urban planning, similar case, using 3D representation. Real estate for the taxes to sell house and whatnot. For public health, like the COVID mapping, right? Like the cholera mapping. The crime mapping, like the hot area for crime, so that the police can have a patrol of on that area more often. And the last one is the national defense for military purposes. Next is still under topic, but concerning the natural world, such as geology, biology, oceanography, climate studies, right? And the last one is the integrated, concerning human and natural world application, such as natural hazard mitigations, wildlife management, sustainable development, natural resources, and climate change response. So these are the applications. If you want to find a topic for your studies, these are the topics, okay, that you can have a look into or study before you apply for your further study. All right. So with that, I thank you very much for your attention. It is a long lecture, but I believe this is uh, be given to you in a recorded form. Um, so yeah, see you in the next GIS class on the second lecture. Thank you.